This is college algebra, and this is unit 6.4, which we're going to be talking about exponential equations. We will explore exponential growth and decay and use logarithms in order to solve exponential equations. The first and most practical example with exponential equations deals with finances. And we've all seen this before, all right? So suppose that you deposit $1,000 called the principal into an account that pays 8% interest per year. We can find the account value after each year and then add it together in order to get what the amount would be if it was compounded. So this is going to be simple interest to start off. Right here is the simple interest formula. So in this example, we have a beginning balance at the end at year 0 of $1,000. Okay, so that's actually what we start with. So at the beginning of year 1, I'm going to transfer that to the beginning balance at January of year 1. And then I'm going to find the interest that I earn over the course of that year. And that's going to be simple interest with the principal of $1,000 times a rate of 0.08, which stands for 8%. Always make it a decimal. And then the time t is 1. So that's 1 year. Time always has to be in years. If I multiply that together, I get an amount of $80. So that is the interest that I would earn on my money if it sat in a bank at 8% for 1 year. In order to find the ending balance at the end of the year, I'm going to add principal plus interest and get $1,080. Well, what if I decided to leave my money in there for another year? This amount gets carried over to the new year, January, the new beginning of the year at $1,080. And now I have to calculate the simple interest again at 8%, so I'm repeating the process. So over the course of year 2, I would earn interest of $86.40. So you can see that after 2 years, it's not that I'm earning $80 every single year. This money has the effect of compounding added to it. And so at the end of 2 years, I would have an amount of $1,166.40. Now, it would be much better instead of extending it to a third year, we could see a pattern in which it compounds every single year, and this becomes exponential. It's no longer linear. And so in order to do that, we want to talk about the compound interest formula. If we invest an amount called P, the principal, earning yearly interest rate R, and compound it for n years, then the interest in the account, the amount which represents the future value A, is given by A equals P parentheses 1 plus R to the n. But we're so frequently used to writing T for n, we can do that as well. So that's another notation. Just a few remarks here. This is a percentage written as a decimal. And then future value is also called the amount, or A. And then N, or T, is in years. An example, suppose you deposit that same $1,000 at 8%. Well, instead of repeating the process for 15 years and doing it over and over again 15 times, why don't we just use the compound interest formula, in which the principal is our initial amount, $1,000, R is 0.08, and now T, our exponent, is 15. We can put this into a calculator and write 1,000 times 1 plus 0.08 to the 15th. We want to follow our order of operations and make sure that you do what's in the parentheses first, and then exponents. So 1.08 to the 15th power gives me a really long decimal. So now this is 1,000 times 3.172169. And times 1,000 will give us a future value of $3,172.17. So notice that in 15 years, you have tripled your money at 8%. Not a bad deal. Here's another example. Suppose you deposit $5,000 in an account that is compounded annually at 6%. Find the future value after 10 years. At this point, I would like you to pause the video and try the problem and see how you can do. All right, here we go. The principal is $5,000. The rate, we have to make that a decimal, 0.06, and then to the 10th power. Hopefully you came up with $8,954.24. So these applications are not just with finances or money, although that's very important. In general, an exponential equation is an equation of the form y equals ab to the x power, where x is the exponent, our variable, and in our application this is going to be time. B is the base, or we can also think of this as the growth rate. And A, that coefficient, we can also think of it as what we started with, the principal, or initial amount. Compare that to A equals P 1 plus R to the T. That's the exponent. This is the growth rate, quantity 1 plus R, and this is our coefficient. So it works. A nice application besides finances would be population growth. In 2000, there were roughly 281 million people in the United States. At a time when the yearly population growth rate was 1.2%. If the same growth rate continues every single year, what will be the future population? So you can see that these terms intertwine. Future value, growth rate, what you started with. So in 2000, the population was 281. Remember, that's in millions. We're trying to find 2045, comma, y. Or we can also think of it as the future value a. So why don't I write a equals p 1 plus r to the t? You can use the same equation. Our initial amount is 281. The interest rate, if you will, is 0.012. So that means our growth rate should be 1.012. And then t is going to be the year 2045 minus 2000. And that's 45 years. Let's see what we get. We get a future population of the United States of 480.65 million people. There you have it. And please comment on this video in order to earn credit, and then have a nice day.